So, yeah, yeah. Hello, everybody. Thank you for coming. So I'll talk to you today a little bit about the stress barrier, about stress barriers and their effect on seismic rupture. This is work we've been doing in the laboratory downstairs recently with Corentin, Federica, and Francois, and also an extra collaborator who's actually visited here. Maybe you saw him, Matthias. So, work. You wanted the problem, and now you have one. I can't even move the mouse. Okay, there we go. Okay. So the way we kind of did this was kind of not, plan the whole thing out originally. We started off looking at an application for geothermal reservoirs, and then we kind of stumbled into more of a fundamental problem that we saw later. And so I'll just put it in that way, the way that we kind of went through it, obviously not in a planned way, but kind of makes the most sense in my head at least. So the first part is an application for geothermal reservoirs. So here we're talking about deep geothermal reservoirs. We're looking at something that's drilled down into the basement rock usually. They drill usually typically two wells, so the doublet wells will be called. You inject fluid into one well, you circulate it through the reservoir, you produce it out of the other well, and this then produces your heat and electricity. The problem is this is done usually through faults and fractures, and these are very tight. So often you have to stimulate these reservoirs by injecting fluid at high pressure. This causes shear slip on faults and fractures. And this shear slip also then has some dilation associated with it. And this dilation allows you to then flow fluid more easily through these reservoirs. The problem is that sometimes this also leads to induced seismicity. There's been cases in France and Switzerland and Korea. And so the idea would be, okay, can we think of some way to do this, have this slip and dilation, because it's basically an earthquake? Can we do this without having then the large seismic event afterwards? And so the idea we kind of came up with is we call it preconditioning. So what we're going to do is basically just play with fluid pressures that try and create a stress barrier such that when we inject fluid, we have this barrier that helps us not have a large earthquake. So I have here a bit of an ugly schematic that will kind of hopefully demonstrate what we're going to be doing. So we begin, we show up on day one with a fault. This fault has a normal stress on it and a shear stress along it. This can be a critically stressed fault, which is kind of the worst case scenario, such that, a small amount of stress change could cause some earthquake, basically. What we do is we then imagine that we drill a well into that fault and we produce fluid out of the fault. So we first require that the fault has some fluid along it. This producing the fluid will reduce the pore pressure in a radius around the well. So this creates a low pressure zone. And through the effective stress law, which I wrote up here, the effective normal stress is equal to the total normal stress minus the pore pressure. So by reducing pore pressure, we're going to increase the effective normal stress in this area. Then we do what people have already done before. We then inject fluid into the reservoir at a high pressure. This causes some slip and some slip front that will then propagate away from the wellbore. This slip front often will overtake the high pressure front. What will happen then in that case, it will run into this low pressure front we created before. And this low pressure front will act as a barrier because it's a high normal stress. So it's a high fracture energy and a low stress drop barrier. And I'm going to talk about what I mean by that exactly right now. So if we imagine a propagating shear frac, like I have here in the darker blue, this propagating shear frac has a cracked tip that's propagating, and it's propagating into some unbroken area, and these squiggles can make some kind of damage zone or whatever you want. And this shear crack is characterized by an energy flux to the cracked tip. This is G here, and also there's a fracture energy that has to come and overcome. It's not exactly a strength, but we can imagine somehow like a strength, such that the energy flux to the crack tip has to overcome the fracture energy for the fracture to continue propagating. So where does this energy flux come from? Well, it comes from the stress drop that's occurring behind the crack tip. And all this is happening in an area where there's some fluid pressure that's there. So what happens when we precondition the reservoir? Well, basically this means that we reduce the pore fluid pressure. So when we reduce the pore fluid pressure, as we just said, that's going to increase the effective normal stress. The effect of that, first on fracture energy. So fracture energy depends on the effective normal stress. You can argue if it's linear or quadratic or what have you, but basically fracture energy goes up as effective normal stress goes up. So by producing fluid out of the reservoir and increasing effective normal stress, we're increasing fracture energy. The second part is the energy flux. The energy flux we think will go down because as effective normal stress goes up, we can think that shear stress is not changing by changing pore fluid pressure. So effective normal stress goes up, and then the difference between the peak shear stress and the residual shear stress has become smaller. So the stress drop is also going to be reduced in this case. And all of this together means that our rupture front is going to have a harder time advancing because the energy flux has been reduced and the fracture energy has been increased. So bringing it back to our diagram, that means that this propagating rupture front is going into a zone now that is harder for it to propagate into, and we hope that this will create some kind of barrier that will stop our induced seismicity, basically. So we're going to now test this idea in the laboratory. For those of you who've been to the laboratory, I'm using the machine that says you go in the door. It's the most on the left. It's kind of the smaller blue apparatus. It's a biaxial apparatus. So these are two PMMA plates here in the light gray, and they're held by sample holders. So this darker gray, these steel sample holders up here. These two plates, in the place where they touch, this interface is kind of our laboratory fault, if you want. And along this laboratory fault, we have a number of sensors. We have strain gauges, spacing sensors, acoustic sensors, accelerometers. So it's a very well instrumented fault. We also have, Francois has a very high-speed camera. And this high-speed camera basically is light that's emitted from these very bright light sources. It goes through a polarizer. It then goes through the PMMA samples. And depending basically on the stresses in the PMMA, this light is basically diffracted. And once it comes out, it's then picked up by the camera. And depending on this diffraction, you can then see you can see where the stress intensity is for elastic material. In this way, you can track the rupture front. So there's no water. So I've been talking about geothermal reservoirs and pore fluid pressure. These experiments are dry, but again, through this effective stress law, we're going to basically simulate these changes in pore pressure through a change in total normal stress. So we're just going to change this. And the way we do this is with our three pistons, our three vertical pistons, apply normal stress. Here they're shown in the red, purple, and the green. And basically these pistons are independent. We can control each one of them individually, and they're also not connected as their sample holder, such that we can really have put a high stress here and a low stress there, for example. That would be something we could do. We have then a fourth piston, which is applying a shear stress or shear force here and a shear stress eventually along the fault. And basically by charging up these three and then this guy, we can then create a seismic event along the fault. So to simulate the precondition we want to do, we first load up these colors correspond to the colors of the piston. We first load up the fault tissue that's kind of in a critically stressed state with these three pistons. Then we also increase this one, make it. We then further increase these ones a little bit more. This creates our barrier. And then finally, we unload this one, this right-hand one. And this basically creates a low normal stress here, which then with the shear stress is going to start slipping. This will create a little earthquake. This will rupture this direction, hit a stress barrier, and then we'll see what happens. So the kind of results that we can get out of this. So on this diagram, I'm showing one experiment results. So this is the y-axis, this is time. This is position along the fault. And there's two things being shown here. One is being shown by this black on white line. So we're going to ignore that for a second and just look at the background. So the background just looks like noise. But actually, if we look carefully, this is the results from the camera. Each line is showing one recording in time. So obviously you can't see the lines, but there's sort of each horizontal row is one time being shown. And what it's showing is it's showing the intensity of the light coming at that location compared to some reference time. And when you basically see nothing, that means that the stress has not changed that location. When you see a shift in contrast, maybe you can see it right here, this a little bit lighter as we go up. There's been a change in stress at this location. And what this does is allows us to track the rupture front. So it's a bit hard to see when it's not zoomed in, but you can actually follow this rupture front as it goes along. Especially when you're on the computer, you can zoom in much more closely and see it better. But this is basically showing us a measurement of our rupture front as it propagates through the sample. Then these black lines, these are data from the accelerometers. So the accelerometers measure acceleration, but by integrating them, we can get displacement. We have 13 of them, and we plot them at the location that they are literally glued onto the fault. So And then when they deviate from that location, that means there's slip occurring at that spot. So for example, this one here is at about a 33 or so centimeters. Nothing is happening, nothing is happening, nothing is happening. Then there's this deviation. And this deviations mean that this accelerometer is measuring something, there's measuring slip that's happening there. And the scale of this deviation, so if it deviates by this much, it means it's 100 microns of slip. So you can see here, maybe, I don't know, there's a 150 or 200 microns of the slip that happened at this location starting at around this time. And we can actually follow them. It matches well with the camera data because we can see this slip started right when the rupture passes location. And something similar up here, for example, you can see again, this is slipping at that point where the rupture passes there. So we do this then for different levels of stress barrier, basically. So we have here no stress barrier, a small stress barrier, and a big stress barrier. And now I've highlighted in blue so you can see it where the rupture front is passing. And so you can see it passes from here to over there at the end of the sample in half a millisecond in this case. And here it's maybe closer to 1 millisecond. And here actually the rupture is stopped. So this is the biggest barrier and the rupture did not make it across the sample. We can also plot slip profiles. So this is again along the fault, addition along the fault, and the slip measured. And the different instances of blue, these are the different times. So initial time is light blue, there's no slip. Then when the rupture front passes, we get darker and darker blue as time goes on, and we get more and more slip. And the black line is kind of the end of total slip that happened. And so you can see here slip again on the right, and then move more to the left. And it's yes, there's most of this location on the left-hand side. And it did make slip on the left-hand side as well. As we show the other results for the other experiments, we have a reduction in slip in this small stress barrier case, and indeed a much bigger reduction in slip when there's a bigger stress barrier. And in fact, it did not slip on the left-hand side of the sample. So this is kind of showing that this stress barrier is stopping rupture, it is stopping slip. And why is that happening? Well, it's kind of going back to what I was saying earlier with, for example, we'll look at this part, the energy flux. This addition along the fault, and this is the stress drop that's measured by the strain gauges. This is the basically the amount of stress barrier. Purple is no stress barrier, darker green is bigger stress barrier. And what you can see is the purple has the biggest stress drop. So it's going to give the most energy to the crack tip, whereas the green lines have the smallest stress drop and even in locations a negative stress drop. So the details don't matter too much, but if we calculate the stress intensity, which is a measure of the energy flux, we can see that there's this the stress drop is right there in this term. It's directly influencing stress intensity. And so indeed, if we then calculate this, we can see that the stress intensity is reduced the bigger the stress drop is. So that's kind of sort of a dry demonstration of preconditioning how we think it should work. And then as we kept going into this, there was a bit more things that kind of came out of it, which may be a bit more relevant for people here maybe. So we'll go into that now. So to start with, a typical diagram of stress versus slip might look like this. So this is obviously very simplified, any details up here, for example, but generally let's say that the shear stress, the shear stress begins at some peak. Shear stress can reduce, this is going to be a linear slip weakening example, down to some residual shear stress, and that residual shear stress occurs for the first time at a critical slip DC, and then is maintained constant. So there's no change in shear stress after that point. And just to give you an idea, because it's always confused me a bit, it's kind of backwards as you imagine the propagating crack. So the peak is obviously near the crack tip, whereas this part, which is far, which is achieved off the slip, is kind of very distal and very behind the crack tip. So now we introduce a quantity, which is breakdown work. So the breakdown work is given by this equation. Basically, what this does, it's the integral from zero slip up until the slip you are under this curve, and then minus this kind of rectangle from the square from the slip location you are right now. So it's the orange area. So as slip goes on, breakdown work increases. So for example, when you have this much slip, now you have this breakdown work, etc. And at a certain point, you reach DC, and your breakdown work is kind of the maximum at that point. And you often see it written as GC at this time. As slip continues, and you're way over here, well, this integral now is not adding anything else to it. So we expect breakdown work to be constant after that point. However, this case kind of depended on this shear stress being this residual shear stress, this constant shear stress. And it's not always necessarily the case that happens. Indeed, you can have something like this, which you might see called like a long-tailed weakening, for example, where this shear stress is still reducing after slip goes on, after DC. And if you do that, then this breakdown work keeps increasing afterwards. And this kind of brings up a question then, okay, basically it's here. Is this additional weakening that's happening after DC? Is this important for energy balance? So I was using energy balance earlier to say the energy flux and the fracture energy, you know, need to be equal to when you have the arrest. But is this additional weakening? Is this to be considered in this energy balance or not? And it's quite important actually, because if it is, it makes things like analytical predictions from LEFM, makes them very not so useful anymore, or less useful, shall we say. It makes it much more difficult. You cannot go into laboratory and characterize your material and say, okay, this material has this residual friction always, so I can then predict whether earthquake will stop. It no longer is going to work that way. And because everything will be connected. Stress drop, slip, and rupture length will all be kind of connected. So to talk about these two cases, the first one is the one I showed you, which is the standard case. It's a conventionally singular driven rupture. It's characterized by linear elastic fracture mechanics, has this straight line, this characterizable residual friction. And the second one is an unconventional singularity, which is then reducing shear stress with slip. So you might ask then, okay, but all this discussion is nice, but do you actually have this? And we do have this. So this is the example from experiments. Each set of experiments is a different normal stress. So these are all different normal stresses that are applied. This is basically the same diagram I was just showing you. This is the slip. On the y-axis, we have this basically this stress drop. And the dotted line is a stress drop occurring at BC. So you would expect if everything was conventional that you would just kind of go down to BC and then just stay along the zero line. And you don't see that because you have this additional weakening that's happening after that initial drop in shear stress. So we have this in our experiments. And you can also see that we have this in our experiments. This is again the breakdown work and the same breakdown work I was showing earlier. Slip and breakdown work as it kind of develops. So it's kind of the area of that triangle as we go on. This part of it is quite normal. We expect this in all cases. This initial part going up to DC. The blue circle is where we have the DC. And then if we were conventional, if we were in this flat case, breakdown work wouldn't increase anymore, which means that it should be some constant line. I drew what it would look like. It'd be some red line there, some flat line. But as you can see, the black data is the real data. You can see that we don't have that. We have something that's increasing still. So we have this case again. So it's kind of a second, they're the same piece of evidence, but they're kind of shown in two different ways. So the question again was, is this additional weakening important? What we will do is we will first find the energy flux that's affected using the entire stress drop. So using the initial DC part and also that long tail weakening part. We'll take everything together and we'll say, okay, all that energy is going to be effective to propagate it. And we'll calculate, this is the energy flux. This is the energy flux as a function of position for these 5 different experiments. So what we have. And we can see, as we expect, the case with no stress barrier has the most energy flux. We expect this already. And as you have more stress barrier, you have more reduction in energy flux. Now the energy balance was, okay, energy flux has to equal fracture energy for the arrest to happen. So now we will just divide that energy flux by the fracture energy. And we expect that when the division equals 1, which is this dotted line here, we expect the rupture to stop. So again, I'm showing the purple is the no stress barrier, green is a more stress barrier. And the squares are where the camera measured that the rupture stops. So the camera is an independent measurement of where the rupture is stopping. And they're plotted here for these 2 green ones, because these 2 green ones stopped. This green one and these 2 purple ones did not stop, so there was no measurement of rupture arrest. And I think the predictions are not perfect. I mean, there's some, so this green square goes with this green line. There's maybe, I don't know, 3 to 5 centimeters of error there, but in general, it's not bad. And at least it's predicting that these 2 stop and these 2 don't stop. If we now do the same exercise where we only take the stress drop up until DC, so we said the long tail weakening is not important for our rupture propagation. It's only this localized, edge-localized stress drop that's really important for us. We do the same thing. Again, purple was no stress barrier, greens are stress barriers. We start to see a problem. First one, we say this one is green one should stop, but it doesn't. These two green ones, this one's not too bad. It's maybe it's a bit worse, but it's not terrible. But this one's quite bad now. His predictions have gotten worse by only considering the initial part of the stress drop. And that was for one set of normal stress experiments. If we now do all of them, we'll end up with this diagram. So this diagram is the predicted rupture length here versus the measured rupture length from the camera. And so it should all fall along this line of one, slope of one. In fact, there's some case. And circles are the case that we took the entire stress drop, and the squares are the case we took only the initial part of the stress drop. And so you can see the circles are not perfect. They're almost not sure. The circles are not perfect. There's a couple of errors, but in general, they're quite close, whereas the squares are obviously much worse predictions. I only have one slide, so it's okay. So basically, in conclusion, to predict rupture arrest, you need to take into account the full stress drop, not just the part up to this DC. And that means that LEFM will not give satisfying predictions when you have this long-tail weakening. And you might wonder, okay, do you just have long-tail weakening in your experiments and not in real life? Well, actually, no, these long-tail weakening things are something we would see often. For example, the dynamic weakening mechanism like flash heating, you'll see it. Also, pore pressure-driven ruptures, such as use seismicity and fluid-driven swarms, they'll also have these kind of these unconventional singularities. And so basically, we already knew that stress barriers would increase GC and decrease this LEFM to get up to the DC value. But now this also is inhibiting this long-tail weakening far behind the crack tip, which is further going to reduce the ability of the rupture to propagate through a stress barrier. So that's all. Very good question. How do you measure